Is that even true?
Yeah.
That sounds legit to me. Okay, we'll see.
You're traveling through another dimension. A dimension not only of sight and sound, but of mind. A journey into a wondrous land whose boundaries are that of imagination. Your next stop,
the Pendulum Zone.
So in this video, we're going to be talking about the movement of a pendulum. The period can be described as when it goes to the highest point on the other side and it goes back to where it started again. In this experiment, we explore the idea that for small angles, the period remains relatively constant. What is a small angle anyway? So there's an approximation that we could do for this arc length right here by using L, the length of the thread, and the angle and trigonometry, and instead of calculating the arc, we just calculate that and use that as an approximation. Another idea that we're going to explore is damping, and what that is in real life, pendulums don't move in like a perfect sine or cosine wave. They actually will kind of slow down over time, and we're going to be seeing if the damping is faster in bigger angles or smaller angles. And another thing that we'll be exploring today is that measuring G. So with this equation here, we can see that we can measure the period, which is in seconds, and we also know the length of the string, so that way we could measure G, which is the last variable in this.
So for our procedure for experiment number 1, testing small angle approximation, we kept the length and the mass of the pendulum constant. We were then able to measure the period of oscillation at various small angles. Because we're able to measure the period of oscillation, we can see when that angle becomes too big for small angle approximation. Therefore, we can find the cutoff point at which small angle approximation no longer works. For experiment number 2, we tested the damping of a small angle versus a big angle. We kept the length and the mass of the pendulum constant as we did in the first experiment, and then we were able to measure the rate of the damping for a small angle versus a large angle based on the comparison of the slope of each of those. For experiment number 3, we tested the value of G. We kept the mass and the initial angle constant, and then we were able to measure the period for various lengths of the pendulum. So we varied the length this time, and then we were able to determine G graphically.
The data for experiment number 1, where we're testing the small angles, we have our data table here where we're comparing the angle that we started with versus the period of the oscillation. And as you can see, the values remain pretty consistent until about 20 degrees. So our expected value based off of the math was 1.285 seconds for our period, which we're rounding up to 1.29, and those values are consistent until 15 degrees, so we're saying that theta is small between 0 and 15 degrees.
The data for experiment number 2, what we can see here is a graph, and it doesn't look like it shows that much, but there's really a lot of information in this graph. So first we can notice that the x-axis we have time, and the y-axis we have period. So as you can see with the top graph, the period is slowly decreasing over time. This effect is known as damping, and that's what we were trying to compare here. So with the graph on the bottom, we have not so much, if barely any, damping. you can tell by the slopes. So the slope on the top line is a lot larger. Well, it's negative, but it's larger than the negative slope on the bottom graph. And this is what we expect. The top line was an angle of 35 degrees, whereas the bottom line was an angle of 10 degrees. And the 10-degree angle is within the small angle approximation. So we expect period to remain the same for the most part.
And then for experiment number 3, we used 2 different known masses. For the first mass, it was 0.3686 kilograms, and we compared length to the period of the oscillation because gravity would be constant. So after some graphical manipulation, we figured for the first test that G was equal to 9.95, and for the second mass that was 2.32 kilograms, we figured G to be 9.56.
Through our experimentation, we found out that the period is constant at small angles, and it's also independent of the angle of swing while it's small angle. So if you raise it up higher, it doesn't change the period.
So we discovered that small angle approximation for us worked at angles less than 15 degrees. It's widely accepted that it works for angles less than 10. As long as you keep your initial angle below 15 degrees, period should be constant.
Through our data, we were able to determine that the bigger the angle, the higher the rate of damping the pendulum will experience. So with small angles, when the period is remaining constant, you're not really experiencing a whole lot of damping, but based off the graph that we had, you can see that the period sort of falls off. Also, we can calculate the acceleration of gravity by using the pendulum and how long it is and the time that it takes to complete an oscillation and compare those graphically.